Okay, thanks, Anna. Um, yeah, so I feel like this presentation is really timely given the sad state of today's winter events. We're actually, the vast majority of the people on this project are either at AGU or out sampling at this very moment. So we're out there collecting data as we speak, which is maybe exciting. But anyway, I am going to talk about sort of how we got interested in this work and decided that it was important, as well as some of our preliminary results. And we've had a lot of support from a lot of different folks, as you can see here, including the Vermont Water Resources Lake Study Center. So as you all probably know, we're used to and like to think about winter, at least here in Vermont, as sort of this cold, snowy period where not much is going on. And this is showing you stream, sort of historical stream flow on the Winooski River, average discharge between 1929 and 1960 with really low flows here, right? And then this is our spring melt going up after the winter period. And the winter period there shown in blue. So historically, rivers and lakes are frozen, ground is covered up in snow, and nothing is really moving from watersheds into rivers and down to lakes. And this is what we're usually thinking about when we think about winter. So everything sort of frozen on the landscape, nothing really moving. But we have these long-term watershed sites that I'll talk a little bit more about in a bit. Then we had to maintain these watershed sites during the winter. We didn't really collect a lot of data during the winter, but we were out there and we started noticing that this wasn't really the case anymore. Where historically cold temperatures and snow and ice kind of kept river flows really low and the water in those rivers very clear, rain and snowmelt were giving us these really frequently high flows, river flows with really silty and muddy water. You can see that in some of these photos here. So clearly some stuff was going downstream, but no one was really tracking it. So nobody really knew what or how much was going downstream. So we decided this might be a problem, or at least it would be useful to know during the winter what was actually happening. And in fact, we did some preliminary data investigation. Um, this is data from the upper Midwest, the lower Missouri River watershed and the upper Mississippi River watershed. And when we looked at those data, we found that winter discharge had nearly doubled since the 1920s through to 19 or 2022. So doubling winter discharge here in Vermont. Our winter discharge from Winooski and the Lamoille rivers, which are the ones that we have longer records for, has increased 50 to 60%. So not as big as the upper Midwest, but still a pretty substantial increase over time. That's not too hard to see. But as some of you may or may not know, winter work is really hard. Everything's frozen. It's hard to get out there. It can be at times dangerous. So no one was really measuring this period, partly because maybe people weren't thinking about it yet, and also because it's just really hard. And sensors are expensive. The sensors that we put in place during the growing season are about 25K each. So we didn't want to put them out in the river in the winter where ice is coming downstream to wash them out and trees and all sorts of issues, maybe getting them frozen. So the sort of the combination of these two things meant that we didn't really know what was going downstream in winter. So along these lines, our group sort of started to think more about this, and we did a data sort of exploration of areas across the US where soils had a lot of nitrogen and phosphorus, and that where those soils co-occurred with really frequent rain on snow events. So our idea was here to figure out, are there places that might be really vulnerable to moving a lot of nitrogen and phosphorus out of the landscape during the winter, right? So we found places where soils were really rich in nitrogen and phosphorus and then looked at how frequent or which of these areas had frequent rain on snow events. And that is the red areas here and the orange areas here. So a substantial part of the US has these nutrient rich soils and also have fairly frequent rain on snow events. So suggests to us that maybe at least 40% of the US could be creating winter nutrient pollution. So all sort of fuel for the idea that we really need to know what's happening out there. And we just didn't have, especially in 2022, very much data to really investigate that. And especially we didn't know, are the sources, nutrient sources, the same during the winter? Are the flow paths the same? Ultimately, just a lot is not known. And this figure, I'm not going to go through it in too much detail, but it was just sort of funny when we were writing this paper. I was talking to a lot of experts, I was trying to make this figure and drawing these arrows and thinking about, in a normal winter, this top panel here, really all you're getting is groundwater. But what happens when you start to get really frequent winter melts, frequent rain on snow events? Do you get more runoff? Do you have soil connection? Do you have water moving through soils and into streams? So I was drawing these arrows and talking to experts, and they were like, you can kind of do whatever you want in these figures because nobody knows, and this looks pretty good. So yeah, this is our goal, is to try to figure out the sources and the flow paths of nutrients during the winter, and if they're different than during the growing season, because that can matter for how we try to manage our systems. So the one thing we did have a little bit of data on was turbidity. So these two figures are showing you the lower Missouri again and the upper Mississippi. So we're back in the upper Midwest, looking at the turbidity or log turbidity by discharge there on the bottom. In the winter, that's these purple lines, versus spring and summer and fall, which are these green lines. Don't worry about this black line yet, but the point here is that during winter, again, the purple line, for every increase in discharge that you get a really steep increase in sediment or turbidity. So this really suggests that we're getting more sediment per unit discharge, getting runoff during winter events. And then for those of you who remember, the 2019 Midwestern US rain on snow flood event was a pretty substantial event. That is what's highlighted right here, and how much sediment was likely carried during that event. So a lot. So our question then was, why might this be happening? Why do winter events seem to behave a little bit different than growing season events? And there are a couple things that we've thought of. One is that plants are dormant during the winter. So we don't have plants actively taking up nutrients and water to sort of stem the flow of water and nitrogen into rivers and streams. The second is the state of the ground. So typically in the winter, you have a snow layer that protects and insulates the ground. If we don't have that, just because of the way we've traditionally managed our agricultural lands, we might have a lot of bare or low cover soils that are vulnerable to runoff. And we also get, without that insulating snow layer, we can get a lot of soils freezing and thawing. If you've ever been out hiking in the winter and seen these ice needles that sort of come up out of the soil, that's freezing soil water kind of getting evaporated and creating these really pretty cool looking ice needles coming out of the soil, but it does loosen up the soil and make it more vulnerable to erosion. So all of this is to say that it really seems incredibly likely that winter flooding has water quality impacts. So when we first started this research in Vermont, we kind of wanted to know two big questions. One is just, how do these new winter events impact nutrient transport? So just how much is going downstream? And then, is winter different than the growing season? What are the nutrient sources and what are the flow paths during the winter? How does it get transported? So we have these two pretty long-term watershed sites. One is Hungerford Brook right here, shown by this orange outline right there. and it's largely agricultural. It's right by Swanton, if you're familiar with that area. And then we have Hungerford Brook over here, or sorry, Wade Brook over here, which is largely forested and is near Jay Peak. These are close-ups of those areas, and we have river sensors. I'm only going to talk about these data, so don't worry about those diamonds, just focus on this yellow triangle. That is where our year-round sensors are in place now. And those sensors, I'll show you in a moment, all the things that they do for us. So again, Wade Brook here, Hungerford Brook down here. So our river sensors that we have in place, this is what it looks like during the growing season. During the winter, they are much more armored than it. But we get information about dissolved organic carbon, particulate organic carbon, dissolved organic matter, nitrate, turbidity, phosphorus, temperature, DO, pH. And then we also do these targeted water samples using ISCOs, which are on automated sampling instruments. So that's actually what we're out there doing at this very moment. So we have data from these sensors during only the ice-free season since 2014, and we have year-round data only starting in 2021. So the first winter that we're covering was the winter of 2022. So we've got 2 full years of data, and now we're working on this winter. So what did we find out about this and nutrient transport? So I will show you some data here. We found out that 30 to 60% of yearly or annual nitrate is coming out of watersheds in the winter. So this is basically percent of constituent. So the only one I'm talking about here is nitrate. So this is the green line in all of these figures. Wade Brook here in 2022, 2023, Hungerford Brook here, 2022 and 2023. So you can see in 2022, we had kind of hovering around 50% of the nitrate coming out of these watersheds during the winter. And in 2023, we had a bigger range, right? Between maybe 30 and 65% of annual nitrate. Whoops. Okay, there we go. I skipped a slide. And then we have a kind of a bigger range, 15 to 55% of annual phosphorus, total P is what I'm talking about here, coming out of watersheds. So again, Wade Brook in 2022, 23, Hungerford Brook in 2022 and 23. And we're looking at these purple lines. So a big range. So this is a little more preliminary data. So looking at how do these winter events affect sources and flow paths? So what are the sources and flow paths for these events? And as I said, these are preliminary results. It's actually fairly complex to try to get this done. We use this thing called an n-member mixing model, which requires a lot of sampling and then a lot of statistics. And we have some preliminary results from that, which are pretty cool. So first, I'm just going to talk about some hysteresis indices. And this is stuff that looks very normal to a hydrogeologist or to a hydrobiogeochemist, which I started out firmly rooted in terrestrial systems. So a lot of this is new to me. So I like to try to put all of these things into sort of easier terms for me to understand. So we have this event hysteresis index, which really just means going from down here on this axis, going from being indicative of distant sources to up here being indicative of nearby sources. And then we have this event flushing index, which on this side is indicative of when nutrients are limiting what's getting into the stream. So maybe there's not enough nitrate to get into the stream. And then on this end, we end up with transport being limiting to the in this case transport of nitrate. So there might be enough nitrate, but transport isn't getting it to the stream. Okay, so that in this quadrant, then we might have nearby sources, which is also sort of um, indicative of highly connected soils or watersheds, stream watershed connectivity, and limitation of nitrate availability. Down here, it's more indicative of distant sources, so low connectivity, and again, sort of being limited by the availability of nitrate. Over here in this quadrant, we're talking about nearby sources and transport being limiting. And here, again, we're talking about distant sources and transport being limiting. So this figure, all the points on the figure, the triangles are wintertime measurements. The circles are growing season measurements. So green is always Wade, the forested site, and brown is always Hungerford, the agricultural site. So you can see there's a lot of variability in what's going on in both seasons. But in general, we've got most of our points sort of down in this quadrant, right? Where we've got sort of distant sources or low connectivity and nitrate limitation. So the things we've been thinking about in terms of why this might be because there's not as consistent fertilizer application during the winter. And nitrate can also really be locked up in snowpack. But there's this question, right? Why do some events have high soil river connectivity or watershed river connectivity and others don't? So this is a big question and sort of leads us into some more of our data that we've got, which will leave us still thinking about this question. Okay, so these are our n-member mixing model analyses. I'm not going to get too much into how we do that, but what it does is partition water into sources. So where is that water coming from based on the characteristics of stream flow and the characteristics of each of those sources. So this is a February rain on snow event. 2023. So you can see this is snowpack. The dotted line up here is snowpack. And then the blue lines here are indicating precipitation. So no precipitation is up here on the top, and then a lot of precip down here at the bottom, right? So some pretty big rainfall events going on there. Okay, and then you can see the response of discharge here with the black line. And then we've got some nitrate data here with the blue dashed line. But what I want to focus on are these different colors. So soil water is red, snowmelt is yellow, sort of yellow-orange, and then base flow or groundwater is blue. So pre-event, right, before flows really spike, we've got groundwater coming into the stream largely, predominantly. So we get this first rain on snow event. We've also got this big drop in snowpack being indicating snowmelt, right? We've got a lot of snowmelt and then some sort of variable amounts of soil water. So some connectivity of the soils to the river. And then in the second event, right, you can see this big snowmelt happening right up here. We've got a lot more snowmelt coming in. And then eventually, right, we basically lose our snowpack here, or most of it. So we lose some of that snowmelt and gain connection to the soils. So I'm just going to show you one more of these just to give you the idea that we've got a lot of variability between events. So that was Hungerford Brook. This is also Hungerford Brook. This is a March melt and rain on snow. So again, here's our snowpack. You can see a lot of rain right here, a big drop in snowpack, and then some more rain. And then again, you can see discharge responding to this rain and big snowmelt event. And then some nitrate data here. Okay, so initially we've got groundwater coming in, but we also this time have some connectivity to soil. So we've got some soil water coming in. When that rain on snow event hits the river, we've got it really dominated by all of this melting snow, but then eventually reconnecting to soil water. So our questions that we're left with, much like those hysteresis indices, are really why are these sources changing across the winter? And we think it probably has a lot to do with pre-event conditions. Are soils frozen? Are they not frozen? Can water infiltrate into those soils? And then what is the snowpack like? Is it really ripe and just ready to run off into streams and rivers, or does it have a high cold content? Um, so we have data on these things that we are currently sort of like dealing with to try to figure out what's kind of making soils contribute more to some events than others, whereas others are more just snowmelt. And then it could also just be the event characteristics, the duration of rain, the intensity of rain, and the amount of snowmelt. So it's likely going to be some combination of all of these things that are driving all of these differences and how connected water is to soils and the watershed in general. Whoops. So the other question that we're going to start dealing with really soon is, are these winter events and nutrient sources really different than those during the growing season? So we have EMAs for these winter events, and we're working at EMAs, the end member mixing models. We have them for these winter events, and we want to get them also for the growing season events and look at, obviously there won't be snow melt, but are river flows much more connected to soils during the growing season, or are they really dominated by rainfall runoff and rain sources? So those are kind of the two directions that we're really heading in. And of course, we've had just a ton of people working on this work that we couldn't have done any of it without them. Lots of great folks involved in this research, including a lot of interns, as well as a whole host of UVM undergraduates who are still working with us and have worked with us in the past.